Hello everyone, my name is Karmuhil. Welcome to today's presentation on eigenfaces. In this session, we will explore the concepts of eigenfaces and their significance in the field of facial recognition. We will delve into mathematical foundations, discuss their application, advantages, and limitations. So let us begin our journey into the fascinating world of eigenfaces. So, what are eigenfaces? Eigenfaces are important for facial recognition systems using principal component analysis to represent significant facial features in a dataset. They efficiently reduce the dimension, extract features, and match faces. Eigenfaces are applied in access control, surveillance, identity verification, and personalized marketing, allowing for accurate identification across diverse scenarios. So these are some of the sample eigenpieces. Here, as you can see, there are original image and their appropriate eigenpieces also. Next is what is PCA? PCA or principal component analysis is a statistical technique used for dimensionality reduction and feature extraction. It simplifies the data interpretation and improves efficiently by identifying significant variation and transforming complex data into lower dimensional space. PCA finds application in image processing, data analysis, and pattern recognition, aiding tasks like data compression, noise reduction, and visualization. Next is face recognition. Face recognition, as we all know, is an advanced technology for identifying individuals based on facial features, using algorithms to analyze and compare facial features. It has applications in security, law enforcement, identity verification, and much more. So next is first we are going to see the approach that we are going to use. The approach I am going to use is first is pre-processing, then construction of covariance matrix, and then eigen decomposition, selecting eigenfaces, phase projection, coefficient calculation, encoding, comparison, and thresholding. So we'll delve into it deeper in the further slides. First is generating eigenfaces. Generating eigenfaces in facial recognition involves several steps. First, the face image are pre-processed by aligning, normalizing their size, and converting them to grayscale to ensure consistency and reduce variation. Next, a covariance matrix is constructed from a pre-processed image, capturing relations and dependencies between pixels, intensities across the dataset. This matrix provides the insights into the variation within the dataset. Eigen decomposition is then performed on the covariance matrix, resulting in eigenvectors and eigenvalues. The eigenvectors representing the principal components, while the eigenvalue indicate the amount of variation explained by the each component. Eigenfaces are selected by choosing eigenvectors with high eigenvalues. These eigenfaces represent the most significant facial variations within the dataset. They can be combined to reconstruct and represent a wide range of facial appearances. Eigenfaces provide a compact representation of facial features, capturing the primary modes of variation in the dataset. This compact representation enables efficient computation and storage, facilitating faster faster face recognition and reducing computational complexity. To perform a face recognition, a new face image is compared with the eigenfaces to identify similarity matches. So those things we'll see further. Next is representing the face. Representing faces using eigenfaces involve projecting the face pre-processed image onto the free space spanned by the eigenfaces. This captures the facial variations encoded by the eigenfaces. Coefficients indicating the contribution of each eigenfaces are calculated through dot product calculation. These coefficients form a compact representation of the face, facilitating efficient storage, computation, and comparison. Accurate face recognition and matching are achieved by comparing coefficients vectors. Eigenface representation enables the efficient encoding and comparison of eigen for accurate identification and verification. Next is we'll do the face recognition part using the eigenfaces. So once we have a database filled with faces and its encoding of the using eigenfaces, we'll start by adding a test case. So in this first the same process will happen. So the test face image will be pre-processed, like converting into grayscale and normalizing it, and then we'll encode it again. So we'll encode it using eigenfaces using PCA and all. So once we have encoded and projected it to face space, then we will find the coefficients. The coefficients are calculated to indicate each eigenface's contribution. Quantifying the eigenfaces And once we have done that, first thing is what we have to do is coefficient comparison. So once we get a coefficient, we have to compare it with the coefficient that are there in the database. So this step is very very crucial for identifying the similarities and potential matches. Next is similarity measure. The various measures such as Euclidean distance or cosine similarity quantify the similarity between the coefficient vectors. These measure determines the degree of similarity between the test phase and the phases in the database, determining the closest match. Based on the similarity measure, the test phase is compared with the known individual in the database. The phase image with the closest matching, having the most similar coefficient vector, is identified as a potential match for the test phase. Next are the advantages. The eigenfaces in the face recognition offer several advantages that make them a popular choice. First is compact representation. Eigenfaces provide a compact representation of facial features, reducing dimensionality and computational complexity in face recognition systems. Next is effective feature extraction. Since it chooses PCA, the eigenfaces capture the most significant facial variation, enabling the efficient feature extraction and representation. Robustness to variations. Eigenfaces are robust to variations in lighting condition, facial expression, and orientation, making them suitable for diverse scenarios. Efficient encoding and recognition. Eigenfaces serve as a basis for efficient face encoding, matching, and recognition, enabling accurate and efficient face recognition. Widely adopted in application. Eigenfaces have been widely adopted in access control, surveillance, identity verification, and other applications due to their accuracy and efficiency. Eigenfaces, despite their advantages, have certain limitations, like sensitivity to light conditions. Eigenfaces can be sensitive to variation in light, which can impact recognition accuracy in challenging environments. Handling complex expressions and pose variation. Recognizing face with complex expression or non-frontal poses can be challenging for eigenfaces. Sensitive to noise and image quality. Noise and variations in the image quality can affect the effectiveness of the eigenfaces in the real world scenario. Assumption of linearity. Linear assumption in the phase variation may limit the ability of eigenfaces to capture intricate details and subtleties. Scalability. Eigenfaces may face scalability challenges when dealing with large databases, impacting computations and storage requirements. In conclusion, eigenfaces have proven to be valuable in face recognition, offering advantages in various applications. They provide a compact representation, efficient computation, and robustness to variations. Eigenfaces enable dimensionality reduction, feature extraction, and accurate matching. However, it is important to consider the limitations of eigenfaces. They may face challenges in handling complex scenarios, variations in lighting and poses, as well as large databases. Despite these limitations, eigenfaces remain as an important component of the face recognition system. Overall, eigenfaces continue to contribute to the advancement in biometric authentication, surveillance, and identity verification technologies. With ongoing research and development, we can expect further improvements and innovation in the field of face recognition. Thank you for your attention.